Hello, my name is Anthony, and this is my Lab 3 report. The purpose of this experiment was to measure how the distance affects the magnetic field due to a bar magnet. The fundamental physics principles were the Biot-Savart law, the fact that the x component of the magnetic field is 0 when facing north, and that the magnetic field is proportional to the distance with the equation B is equal to k times r to the power of n. The models I used are that I placed a bar magnet at the end of a meter stick and moved the phone along the meter stick, and then I used a code to model the actual experiment. For the results, I found n equal to negative 2.6721, and I found the value of the magnetic field when the observation location was at a 45-degree angle and that distance to be 3.8321 times 10 to the negative 5 teslas. I used a code to model the experiment, and the code uses the Biot-Savart law, shown here, to calculate the magnitude and direction of the magnetic field at any observation location. The code also uses the magnetic moment of the bar magnet, which I calculated in the experiment, and at the end the code finds the computational value for the magnetic field when the observation location is 0.206 meters away at a 45-degree angle, and this computational value will be used to compare to the experimental value. For the experiment, I made the assumption that the magnetometer app did not experience any magnetic fields other than the Earth and the magnet, and this made sense because the x component of the magnetometer app was 0 when the phone faced north, and also because there were no other magnetic objects nearby. Also, in the experiment, the phone was the system, while the magnet and the Earth were the surroundings, and the initial condition was mu0 over 4 pi. For the first part of the experiment, using the magnetometer app, I placed the phone so that the x component of the magnetic field was 0. This meant that the phone was facing north since the Earth's magnetic field runs north-south. Then I placed the meter stick parallel to the phone, as shown in the image, and I placed the bar magnet at the end of the meter stick. I then found where in the phone the magnetometer sensor is, and I used this to calculate the distances at which b of x equaled these values. I also used 3 trials for each. I used the data to plot this graph. Since the equation is b equals k times r to the power of n, taking the ln of both sides allows n to be equal to the slope of the equation. Therefore, n is equal to negative 2.6721. Also, using ln of k, which is the constant, I was able to figure out the magnetic moment to be 3.568 amps times meters squared. For the second part of the experiment, I used the same setup as from part 1, and I found the distance at which the magnitude of the net magnetic field was equal to 100 microteslas. I recorded the y component here as the magnetic field of the Earth. Then I placed a second meter stick facing north-south at this distance, and I moved down the same distance on the second meter stick. Here I recorded the x, y, and z components and subtracted the magnetic field from the y component to get the net magnetic field at this observation location to be 3.8321 times 10 to the negative 5 teslas. Now for the code, the link for which is in the description. The first part declares the initial conditions, and the next part sets up the magnet with the experimental magnetic moment. The next function calculates the magnetic field, and afterward some observation locations are set up and their magnetic fields are calculated. The final part of the code calculates the observation location that is at a 45-degree angle from the magnet, given the d-perp value from the experiment. Here is the output of the code. The magenta arrow is the 45-degree magnetic field arrow, and the magnitude of this arrow is 6.2155 times 10 to the negative 5 Tesla. Now, if I hadn't set up the meter stick so that they were running north-south and east-west, it would have made the experiment a lot harder because the magnetic field of the magnet and the Earth would be in both the x and y components. This would mean to find the magnetic field of the magnet, I would have to remove the magnetic field of the Earth from both components using the angle theta, but if done correctly, the results would be the same. However, if the magnetic field of the Earth is not removed, then the observed magnetic fields and recorded distances would increase. Now, if I were to stick 2 identical magnets together end to end and run the experiment again, I would expect the magnetic field experienced by the phone to increase, but by a little less than 2 times. This would mean that the recorded distances would also increase. However, since the 2 magnets can't take up the same space, the magnitude of the 2 magnets would be a little less than 2 times greater of that we determined in this experiment. From the experiment, I was able to find the values for n and the magnetic moment. Furthermore, I was able to calculate the experimental and computational magnetic fields for the 45-degree observation location as shown. Both the model and the experiment had the same assumptions, observation location, and magnetic moment, so the same setup. However, The model calculated the magnetic field using the Biot-Savart law, while the experiment used the magnetometer app, which is why there's a difference in the values. Furthermore, the experimental value has some error due to human error. This came from recording the distances during the experiment and also from the fact that the meter sticks were likely not exactly perpendicular and also not exactly east-west and north-south. However, overall, the experiment was successful at finding good approximation.